Hello, everybody, and welcome to another wonderful day of chemistry. So today we're going to relate Gibbs free energy to chemical potential. So one of the first things that's worth noting is trying to denote what we actually mean when we're saying electrochemical potentials and what we mean when we're saying Gibbs free energies. And we can go ahead and use this to relate the two properties. So for example, let's go ahead and look at, say, a simple reaction like the reduction of iron 2 to iron solid. Well, this has a reduction potential of negative 0.4, meaning that this reaction doesn't really want to occur. Because what it really means when I'm reading that E naught is how much excess energy each individual electron possesses to make the reaction go forward. So if I've got a negative potential, that means it has negative excess energy, as in I have to put in energy to make the reaction happen. And again, this is how much energy each electron will have in volts. However, if I go ahead and take a look at our good old friend Gibbs free energy, well, this would tell me how much energy this reaction requires. So I know that this reaction requires energy. So while it has a negative potential, I'd expect it to have a positive free energy because I have to put energy in. Also, instead of energy per electron, I'm looking at energy per mole of reaction. So reactions instead of individual electrons. And then again, there's also just the whole process of units. Potential is in volts, Gibbs is in joules. So I have to go ahead and remedy these three main issues. And we can do this using our Gibbs relation equation. So it's broken into three major features that we can use to relate our potential to our Gibbs free energy. And it's worth noting this holds for reduction potentials, oxidation potentials, or even cell potentials. So the first important one is we need to flip the sign. A favorable electrochemical reaction has a positive potential, but a negative Gibbs free energy. So we have to address that by flipping the sign of the system. The second big thing is the number of electrons per mole. Because, for example, our potential means that we're looking at the energy per electron. Well, I've got 2 electrons per reaction, so I've got to double that amount of energy because 2 electrons are participating. Go figure. And then the last one is this constant F. This is just unit conversion. It is a way to convert from volts to joules. However, it's a little bit of an odd one. And it's so special, we give it its own name. It's called the Faraday's constant. And you'll often see it reported as about 96,000 coulombs per mole. And coulomb seems like a very weird unit until you note that it's just going to be joules per volt. So really what we're looking at when we're talking about the Faraday's constant is we're taking that potential in volts and we're turning it into joules per mole. So a lot of people ascribe different meanings to Faraday's constant, but I just tend to think of it as simple unit conversion. If you don't know how to go in between volts and joules or kilojoules or kcals, go through Faraday's constant. It will get you to the right place. So one of the reasons why this is important is that by looking at what we already know about Gibbs free energy and applying it to a chemical reaction, we can figure out a lot about how we can modify our reaction equations and what that will do to the potential based on what we know that it does to Gibbs. So for example, let's go ahead and take the reduction of our iron 2 ions. And let's just start by trying to figure out the Gibbs free energy. So notably for this reaction, we've got 2 electrons. So we're going to need to double the Faraday's constant times the potential. So it turns out this will give us an answer in about 85 kilojoules per mole. So again, worth noting, I went ahead and just casually converted joules to kilojoules. If you need a little bit of help, you can also express Faraday's constant in kilojoules per mole by simply turning this comma into a decimal point. It's about 96.5 kilojoules per mole volts. So now that I've got the Gibbs free energy, let's go ahead and see what we can do with it. we can use it to help figure out what the potential of the reverse reaction is. And so we know that this is just the oxidation reaction, so it should just flip the sign. But let's go ahead and prove this. So I know that if I go ahead and flip the reaction, that will flip the sign on Gibbs free energy. So the Gibbs free energy for the oxidation of iron into iron 2 should just be negative 85, meaning that this oxidation reaction will be quite favorable. And then I can go ahead and take that Gibbs free energy, plug it back into my potential expression. So I can find the potential by taking my new Gibbs, dividing it by negative NF, and ta-da, we get back 0.4 volts. So again, flip the reaction, flip the sign of the potential. So exactly what we saw last time, but now we showed why it occurs. Now let's go ahead and figure out, if I take my iron reaction, what's going to happen to the potential if I double the reaction coefficients. So instead of going from 1 iron, 2 electrons, 1 iron, to 2 irons on both sides and 4 electrons. Well, we know what this does to our Gibbs free energy. It doubles it. I have twice as many moles, so I'll have twice as much energy per reaction that occurs. Ta-da! We know that. Now let's go ahead and back calculate the potential from this expression. So we'll again divide by negative NF. Now the big notable thing here is that now in this second reaction, I'm transferring 4 electrons instead of 2. So as a result, when I do that, I get back negative 0.44 volts. So this is actually quite a cool phenomenon, that if you end up changing the coefficients of a reaction, it doesn't change the potential. It will change free energy, but the potential doesn't care, because the potential is the amount of energy per electron. And if we double the reaction, the amount of energy per electron doesn't actually change because we have an internal reference. So this is a very useful thing when trying to manipulate reaction equations. It doesn't matter whether I'm reducing 1 iron or 20, it will always have that same exact potential, which is very useful for a lot of purposes. Now let's go ahead and figure out how we can combine multiple reactions of known potentials. So if I know the potential for, say, the reduction of iron 2+ to iron solid and iron 3+ to iron 2+, I can combine these reactions to try and figure out the reduction potential for going from iron 3 to iron solid. Now, the tricky bit is we know how to combine potentials if I combine a reduction reaction and an oxidation, because the electrons go from one reaction to the other, the electrons cancel out. We're not so lucky here. And we run into an additional problem because this is the energy per electron, and each of these reactions has different electrons, 2, 1, and 3. So I can't just simply add them together. However, I can do that with Gibbs. The Gibbs free energy for this third reaction is simply going to be adding these 2 other reactions together. So I can get my Gibbs free energy for my third reaction by adding the first reaction and the second. And if we find out that the reduction of iron 3+ to solid iron is going to be slightly unfavorable. I have to put in a little bit of energy. And so as a result, when we go back to the potential, one of the big things, note, is we flip the sign. So I will have, again, an unfavorable or slightly negative potential. And again, watch out, we're going to have to divide by 3 electrons because the product has 3 electrons. So if you need to combine reactions, turn your potentials into Gibbs, combine the Gibbs, and then go back to potential. It's a couple extra steps, but it always works. And it is worth noting that there's going to be a lot of electrochemical reactions that you can't find the potential any other way. If you want to go ahead and find this very common reaction, the formation of iron solid from the quite common iron 3+ ions, it is actually not in most reduction tables. Instead, you'll find these 2 reactions because chemists, being lazy, anticipate you doing the work for yourself. I'm sorry. So now that we've got a better idea of how Gibbs pre-energy and reduction potentials work. Next time, we're going to go ahead and figure out how potential can be modified by concentration using our good old friend Gibbs. Till then, take care.